Okay. Let us continue our lecture. So in the morning lecture I start on this slide. So we have considered the effects of contact and material properties on the melting current in two different cases. If you look again, just to recap our knowledge, you see that the melting current is proportional to the AH, and this is AH. This is the area of the electrode, bottom electrode, or its heater in this case, and it's also proportional to the LH to the length. But according to this equation, you can see that if you want to reduce the melting current, we can use the smaller size of heater, or we can increase the length of our heater. The second case is maybe not feasible, because if you increase the size of the heater, you need more current to go through the heater, because the conductivity of heater is also not so high, so it will be a limited factor. What we do, we will reduce the size of the heater, the working area of the heater. In this case, also in the second case, we can reduce the switching volume in the case of GST layer. And then, if we will also consider later in our lecture, we can also try to adjust the material properties like K of GST material, and also we will see the influences of KH and rho H on the switching of the device. So let us look to the different type of devices. In the literature you find different structures, and they are categorized in three types. One is contact minimized cells, second is volume minimized cells, and three, this is hybrid cells. So the contact minimized cells, they are based on this equation, so you are trying to reduce the contact of your device, and the second, volume minimized, you try to reduce the volume of your phase change materials. And of course, you can think about how to combine this, the benefits of two cell structure design to get the best benefit of your device. So to contact minimized cell, contact area between the heater and PCM is minimized. And the reduced cross-section of the heater determines the high current density required to heat up PCMM, and it acts as the external source of heat built-in heater. Volume minimized cells, as I said, it's confined. We confine the volume, and phase change in volume minimized cells is corrected primarily by the power dissipated in the confined chalcogenide volume diajoule heating. This is cell-heated cells. So as I said, you will find in the literature different types of the cells. One is, we considered already, this is so-called laser cell or mushroom cell. Mushroom because if you switch your volume in the cell, we can try to show you here. We have two contacts. This is contact. This is PCM. Okay, and this is the bottom contact, bottom electrode, top electrode. And now if we, and here we have heater, here heater, bottom electrode. And now if it's crystalline, we start with crystalline, and if we apply a pulse and amorphize this structure, we get like volume like this shape, of this shape. And now if you look here, it looks like a mushroom. And that is why it calls mushroom cell. So here, if you want to optimize the contact area, you have to reduce the size of the heater. The second, this is wall cell. So here, this is also the same actually, but here you minimize this is the heater. It's a special made heater, so it's like a wall. So it's not like a here round shaped heater. This is really it goes like a wall. This is because of the lithography. Then there is also mid-range cells. Here you also minimize your heater contact by doing special design of contact. This is bottom top view. You see here this is the contact here, and this is the side view or cross section. You can see that you minimize here contact to your PCMM, the phase change material. In the case here also there is a cross spacer device structure. Here actually same as mid-range, but here your heater is connected to this both small heaters here. In the volume minimized cells, these are self-heated PCMs. Here you minimize the volume of your phase change materials to reduce the melting current. Similar like to mushroom, but here you don't have the heater. In confined cells, it's pretty also the same. You replace here the heater by phase change materials. You can also make a planar line bridge cells. So you have here your phase change material, and you minimize the switching volume here by making a line. And here you have two contacts, two electrodes. You can also make, as I said, mixed cell and make confinement of the electrode and of your switching volume. And this goes like dash-typed confined cell. Here you reduce the size of your phase change material, and this is the size of your heater. And here from left and right side, this is silicon oxide. So now let us look to the performance of different cells. If there are differences in the performance between contact minimized or volume minimized or confined cells. So here I summarized the data for different. Here this is the reset current in μm, and this is the node size. So this is the size of your cell, which can be achieved by lithography. So what we can see that in mushroom cell, this is before it was standard cells, you can reach different currents, but by reducing F, the node, you can get like currents like on the average of 100 microamps. This is, if you remember from the lecture today morning, we need the currents in the range, reset currents in the range of 200 microamps, and if you can here make lines, you will see that different type of technologies can meet these requirements, and different companies tried different different types and found that there is differences, but also the differences lies also in the not only in the contact, but also in the reset current used. As you can see, this is the cross spacer cell, different contact area, different reset, different length of the pulse, like 50 nanoseconds or 500 nanoseconds, and you see that in one case you need less current, and in another case more current. So if you use shorter pulse, you need more current to switch your cell. If you use the longer pulse and a little bit larger area or smaller area, you can get a little bit smaller reset current. So different technology, but the results are the same. So if you make the line here, you can get this 200 microamps with different technology, and by using different scheme of switching, as mentioned by Shivendra in the talk before. Here, this is also one cell, integrated confined cell. Here you see this is a volume minimized cell and contact minimized cell. And here you can, the researcher, they get the reset current smaller than 100 microamps. Cycling endurance here, it was 10 to the 7 cycles. Set current 150 nanoseconds, and the device was operating at 1.8 volt. It was actually produced by Samsung, and it was 8 gigabyte PRAM cell using this 4F2 technology on 20 nanometer node size. As I said, you can try to improve your contact area by minimizing the contact itself, by heater itself. But the commonly used heater material, this is titanium nitride, and the conductivity of this material is limited, and it's not so large as we want. It's like 12 milliwatts per. And just to increase, to improve the heater, the properties of the heater, what you can use in nanomaterials like CNT. This is carbon nanotubes, and you can integrate it in the device and look. So if you use a standard heater to titanium nitride, you get the current density for switching like 24.3 mA per square centimeter. But if you use improved heater using CNTs, which has higher conductivity, then you get the values like on the average 0.7 mA per square centimeter. Here they used also pulse duration 5 nanoseconds. We want 100 seconds, but just to achieve this value, they needed to use it. Endurance, it was 10 to the 4. It's also not good, but it was scalable in the whole diameter. This is also line cells used based on the GST and different electrodes. And here, by optimizing this, by making very small electrodes, like here, cross-point cell, vertical cross-point cell, or here in the nano gap, you can also achieve here very low energy consumption, like 1.2 picojoule per bit, with 450 nanosecond reset pulse. It's very nice, but the endurance here should be improved here in this case. So there are huge development in this direction. There are many ideas, but it's the integration of such scheme. It's still maybe a topic for the next year. So here, how to minimize programming power. Also, there is another also ideas like using CNT electrodes. In this case, they are integrated into standard technology by replacing the heater. In this case, they used the here CNT's electrodes like in this scheme, and they put the PCM in between. It's also based on the lithography, so they can make a gap between the electrodes, like in a range of 20 to 300 nanometers, and they can also vary the CNT diameters between 1 and 6 nanometers, so they can reach the reset current very low, like 6 μA with 50 nanoseconds, set currents in the range up to 0.4, the pulse 150 pulses, very low power consumption, but the endurance here, as you see, it's only 200 cycles. So it's nice concept, but it needs to be improved. And also some also very interesting new idea to use as electrode, to use, for example, graphene instead of CNTs. Use the graphene as 1D contact, Here you can use like 3 nanometer wide graphene nanoribbon as a contact area, and this is a very low cross section of each contact. Here again you can reach very small reset currents with 100 nanosecond pulse, very low power consumption, and endurance here. It's also nice 10 to the 4, and of course it should be improved. There is also one concept. We have also many nodes on the problems of PCMs. One is the resistant drift, that the material itself it can change resistance during the time. And to overcome this issue, in recently 2023, it was by IBM, they proposed a so-called projection phase change memory device to reduce the drift of GST cell, of a PCM cell. And here they used different read scheme. So the cell operates like a normal cell. You switch between high resistance state and low resistance state, but you read, let's say, in projection here, in projection segment, and then you can, by using this, you can reduce this problem, the drift current. Now to the another device architecture, to the 3D point. Also, Shivendra here mentioned that we need to make our memory more denser, and that there was development of Micron, ST, and Intel in the direction of high dense phase change memory. And in this case, the scheme is a little bit different. So they use, first they use, if you think about technologies, if you want to make the dense on our memories, we go always in the vertical direction. So here we see one 3D X point with 2 cells. Here one row, and this is the second row, the small cells. This is like one resistor, one selector. And here we don't have the heater. In this scheme we have a selector which selects the state of our GST cell. So here the development was in the direction of to how to get a very nice selector. In this selector that should provide a high current density on this order 10 to the 6 ampere per square centimeter to reach this 3D technology. It should be also has a high endurance and high on-off current ratio. So you can see here, this is the GST cell, this is OTS, this is selector, and bottom electrode work line cell. So the development was started in 2010, and it was continued at 2021, and there was also many products based on this 3D. Maybe you heard about this. It was Optane technology, so Optane memory. And they used it for some mobile station for notebooks. They put this memory as additional like RAM memory to speed up your system. So now let us look to the current density required to switch between the different memory cells. So if we consider our design of the cell, like here, heater, this is bottom electrode and top electrode, and this is the GST here. So we need, first of all, we need to consider one issue, like the distance between each cells. because the switching is based on the Joule heating, and the areas surrounding the GST is also heated. And if we place the cells very close to each other, we can affect the next cell. So this is the problem with reading and writing the next cell. So in the technology, the distance between two cells is defined like 2f. This is called like this is a footprint. And according to this, to avoid crosstalk between the cells, this f, it should be larger than square root of 2dt. D, this is the diffusion constant, defined as K divided by dCp, and Cp, that is specific heat, and K is thermal conductivity, time is the time duration of the applied electric pulse. Now, if you so just think about it, the expected pulse duration from the above equation to satisfy the minimum condition that the supplied energy should be large enough to rise the temperature of the critical value above the melting point. We get this equation, and now this is the yield, this is the current density, and rho, this is electrical resistivity. If we put some material values to this equation, if we find that we need a high current density to switch the volume of our phase change memory cell. So it's on the range of 10 to the 7 ampere per quadrat centimeter, or it's to the 10 to the 5 microampere square micrometer. And this is current which is needed to melt the critical volume within the cell for reset. If we also compare the critical current density to switch like magnetic ROM, I did some estimations, and I found in the literature if you use 100 picosecond short pulse, 100 micro strong current pulse, we get also the values even larger as needed to switch the PCM. So if we have such a high current density needed to switch the volume, it can bring the cell to some issues like that. If you switch the cell for many times, like to the 10 or 9 cycles, what can happen here at the side of the heater, that here at the contact area between GST and heater, some holes can be produced, and so you lose the contact and you cannot switch the cell back, forth and back. So this is one failure mechanism. It's based on void formation in the electrode, and another problem with such high current density you needed. This is the elemental segregation. In particular, antimony enrichment in the switching region caused by electromigration, and this can lead to the poor data retention. Then the cell can no longer be switched to the high resistance state, or does not retain in the high resistance state, since antimony rich alloys have low crystallization temperature. But somehow it's very interesting. This is not an issue in the very confined cell. If you confine your materials to the, this is the size of like 7.5 nanometer, and this cell was cycled to the L cycles. You see the elemental segregation, antimony here, antimony rich here, the volume rich. Here there's like a mix, more antimony. But in this case, it's somehow the cells can be still work, and so it seems to be not the issue if you reduce the size of the cell. Now there are also some other concepts on the how we can switch our cells. One is based on the phase change between crystalline, amorphous and crystalline phase. but as I said before, there are several issues, so we need high current density. The structure is complex. We need lithography. If you want to make some test cells, you need this facility. There is volume change and resistance drift after reset. So the next, the second idea, what we can use instead of just to switch in between amorphous and crystalline, you can use so-called conductive bridge, random access memory. This is the second alternative to the normal cell. And here we have, as I said before, dissolution of anodic dissolution and cathodic reduction of metallic filament. But here we need a chemical electrode. So just for recap, how does it work? If I have here active electrode, we form first the filament, and then we can, by forming and destroying the filament, we can get a low resistance state or high resistance state. Here, this is the very simple structure, and it can be realized in many laboratories. There are also some prototypes, some devices made of such CBRMs. One is based on the kappa top electrode. This is the germanium selenide switching layer. So you see here kappa, germanium selenide, and tungsten electrode. And so the size of the top electrode was pretty large, 200 nanometer. And here you can operate the cell like by bipolar switching. You can switch in one and then in our direction with power operation like 200 microamps, 1.3 volt. It has a nice resistance ratio and can be endurance can be 10 to the 5 cycles. And here the switching mechanism is formation and dissolution of copper filaments. Also, you can also build a phase change device based on the silver electrodes, like silver, antimony telluride, and platinum. Here you can use a little bit larger top electrode, like 200 microamp. Here you also reach bipolar resistive switching, but the resistance ratio is not good, only 5. Nice endurance here. Set reset voltage is also low, and switching mechanism based also on formation and dissolution of silver filaments. In the area of this germanium telluride, also you can use copper as electrode, and then you can also get a nice value for set and reset, like plus minus volt, and it's also bipolar switching, and the resistance ratio 10 to the 4, also nice. In our research, we also tested some different electrodes for GST. We used these electrodes: aluminum, titanium, chromium, tantalum, cobalt, copper, silver, gold, platinum, and chromium. And depending on the electrodes. So here the inert electrodes, they do not have do not show the switching. Chemically active electrodes like copper, copper, and silver, they have stable switching, filamentary switching. Chrome also shows some stable filamentary switching. And here aluminum, titanium, they also can be used, but they showed the degradation here. And titanium too. You can use, if you think about the problem of resistance drift, instead of using amorphous to crystalline phase change, we can use epitaxial thin films. They are fully crystalline. And here we also make some tests using epitaxial thin films. We constructed CBRM consisting of silver top electrode, epitaxial thin film, and P silicon. And we here found a nice bipolar switching using silver electrode, very low set voltage, reset voltage, memory window 100, but here we don't need no current compliance, and we don't need here format voltage. In the case of oxide CBRAMs, you need to make first the filaments and then draw program, but in this case you don't need the forming voltage, and this is maybe some advantage of this. Also, we tried such cells for neuromorphic computing, so we studied potentiation and depression. This is similar to the multi-level capability of the cell. So we have applied here pulsed voltage plus and minus 0.3 volt with pulse duration 100 microseconds, and we could see that the current can increase independence on the pulse number and then decrease. So this is such a cells, they have potential for application in neuromorphic computing. So summary on the of this technology of memory device architecture, it's given on this slide. For F is defined as the smallest 2D feature in semiconductor technology. F, this is node size, the smallest feature, the smallest dimension a CMOS lithographic process can create. A stack n layers in 3D reduces effect cell size and reduces production cost. So if you can stack more and more layers, you can reduce the production cost. To be competitive with NAND, PCM has to produce with 4 F2 memory cell size and MLS compatibility. The thermal diffusion length should be not exceed the half pitch distance F in order to avoid crosstalk during programming of PCM cell. Due to amorphous to crystalline transition, a high reset current is needed to melt crystalline phase. Reduction of melting time can be achieved by scaling PCM dimensions like heater size and PCM F size. Current density on this range level is required to melt the critical volume inside the PCM. And to reach such high current density, the volume threshold switcher are used in 3D X-point technology. OTS is also applied as selector for each PCM cell. 3D X-point cell has 4 F2 memory cell size with node size 20 nanometer. And material parameters also impact device performance. We will consider this in the next lectures. And voids at the bottom electrode contacts and elemental segregation of failure mechanisms of PCM cells. So here I stop at the first lecture. If you have some questions, you can ask now, or maybe we can shift it to the end of this lecture. So, do you want to ask something? Okay, then we can continue with the second lecture. So the second lecture is about the properties of chalcogenide materials for non-volatile data storage. And here in this part I will consider optical and electrical properties of the materials. So I think this is the basic properties what we need to know. And if we know this, we can optimize our material. So we know already a little bit that performance of PCM devices is based on the significant change of optical and electrical properties during the phase transition, and this should be carefully controlled. For the efficient development of PCM technology, we need to understand these optical properties and the electrical properties, and in this part of my talk I will focus on the discussion of optical properties and also on the electrical properties. So now first let us consider the optical constants and optical band gap. So if you want to construct a device, optical device, we need to know the optical properties of each layer. Like here in this optical race track, we have here optical waveguide based on silicon nitride, and it consists of stack of GST and ITO layer on top. If you think that the optical properties of this stack system defined by each layer, we need to know the optical properties of every layer. And we need to know the properties not only in reflection, but also in transmission mode. So if you know these properties, we can calculate the reflection spectrum. For example, if we're interested in the reflection from this layer, we can calculate this, and then can design a device, optical device, which we need. So we need to know optical constants like N and K. This is N, this is refractive index, and K, this is excitation coefficient, and they both describe how the material interacts with light. Please remember that the optical constant depends on the wavelength and photon energy of excited light, and so they are not really constant. They are constant at particular wavelength and particular photon energy. So the refractive index indicates how much light bands then enter a material, while the excitation coefficient quantifies how strongly the material absorbs of light. So the excitation coefficient is somehow related to the absorption coefficient, like by this equation. It's equal to the phi pk. This is extinction coefficient divided by wavelength of the incident light. And here this absorption coefficient, it can be measured by different techniques, and it can be extracted from this equation. So this is I equal to I0 exponential minus alpha x, and this means that if light of initial intensity propagates a distance x in the material, that intensity decreases from I0 to I. So now let us consider how to measure this absorption coefficient. There are two famous techniques how to do it. One is UV with NR spectroscopy. This is ultraviolet visible near infrared spectroscopy. And second, this is spectroscopic ellipsometry. So UV, this near spectroscopy is a technique used to determine optical properties like reflectance, absorbance, and transmittance of liquids, and also the solids. So it's based very simple technique. So you have your system like substrate and thin film or bulk material or liquid, and then you illuminate your material with the light, with intensity 0, and then because of absorption inside of your system, the intensity of the light is changing. Here, this is IET, this is transmission, and of course you have some reflections in the system, especially at the interfaces. And this transmission is defined like 1 minus R exponents minus alpha t. R, this is the reflections, as I said. And from this you can rewrite it, and you can find the absorption coefficient, and then you can calculate band gap and the K excitation coefficient. So in this technique, what you get like data either plotted as absorption against the wavelength, or like a transmission against the wavelength, and then by using I will show equation, by using this equation, you can transform the data and to calculate the band gap, and you can find the basic property of your material. But there is a problem in the case of thin film. If you want to measure, you can have a multiple scattering inside of your system, like at the interface or at the surface. If the thin film is not flat, then you can get troubles with your examination of your data. So the spectroscopic ellipsometry, this is also nice method because it's not destructive, non-contact, a non-invasive optical technique, similar to UV spectroscopy, and it also measures the optical properties of your materials, like refractive index N and excitation coefficient K. The basic principles is based that the ellipsometry measures the changes in the state of polarization of light upon reflection from the surface, and it measures changes in polarization state of light, like difference in phase shift and ratio of amplitude change. So if you again illuminate your thin film or your system by the light, it can change its polarization, can rotate, and so the two components EAP and ES, they can change their direction. Like in this case, it will be parallel. Here, this is perpendicular to the light, and this is now after changing, it rotates, and now it's parallel, and this is perpendicular. But in many cases, you don't have the rotation of your light, so you use special system to use the rotation, or to make the rotation of your electromagnetic wave before to put this wave on the film. So then in ellipsometry you get like the angles, sigma and delta, and the plot of this angle against of the wavelength, and then you need to make some numerical simulations, use different models to fit the experimental data to the simulated data. And from this you then can get the basic properties of material, like optical constants for GST. Here in the visible and near infrared region, the constants are significantly different between amorphous and crystalline phase change materials. So if we consider this graph, you can see this is the K for crystalline excitation coefficient, and this is for crystalline, and this is for amorphous GST. You see the differences, and then this is because the same for N. So you have the difference in absorptions and in the reflectivity. Also, we can see here in the absorption coefficient map, this is photon energy, this is absorption coefficient, that the different phases, like amorphous phase, it's less absorptive than cubic phase and trigonal phase. So these are both two different crystalline phases. We will learn about these phases tomorrow. In the near infrared region, we can see also differences in excitation coefficient. So like this is for S-deposited amorphous, and this is for crystalline. So for amorphous it's lower than for the crystalline. Transmission is also, you can see here that for S-deposited it's transmit more light than the crystalline. So from here we can already learn that this phase is more reflective as this. The interesting for optical communication, which is in the range of 1.5 micrometer, that there is also difference between amorphous and different crystalline phases in transmission. It reflectance also. So optical constants for crystalline GST225 phases depends on the structure. It's written heating, but it's on the structure. So it hints on the defects and disorder of optical properties. Transmittance reduced from amorphous to crystalline phase change and differs from crystalline phases, and reflectivity increases from amorphous to crystalline phases. Here we can see more example on these different properties of materials. As I said, especially in the crystalline phases, so phase change materials like GST225, it has three different crystalline phases. One disordered, highly disordered, one is more ordered phase consisting of van der Waals-like caps, and here this phase, like in between, where these vacancies, which are here high number, this phase contains high number of vacancies on cation sublattices up to 20%, then can be ordered here as these dark lines, and so we can get different structures. They were known as epitaxial thin films, and first we can see differences in the reflections of these phases, like amorphous. This is low reflectivity phase, and crystalline phases. This is the highly reflective phase, and because there is a differences between the crystalline phases, so we can use it like it has potential for novel switching concept and for multi-level capability. Imaginary part of the electric function, it's also different for amorphous and for crystalline phases. So again, we have here different absorptions, and this is because of the two difference in carrier mobility of the various phases. So now to the optical band gap. So optical band gap of semiconductors is determined by the onset of optical absorption that occurs when the photon energy h nu of excellent light just equals the energy separation of the highest occupied electron states in the valence band and the lowest empty electron states in the conduction band of the semiconductor. So the absorption coefficient alpha and the band gap of semiconductors generally follows these relations. This is alpha h nu constant, h nu minus Ag. This is the band gap, optical band gap, and this is R. This is the exponent which we have to select for fitting. Now, if this relation holds, then E optical Eg is found by linearly extrapolating the plot of alpha h nu, this h nu, and finding the intersection to the axis. So here you can fit your data, and then from transmission from UV nis spectroscopy, and then by drawing the line and by intersection with abscissa, you can find the band gap. So for crystalline and for amorphous GST, the band gap is around 0.7 eV, and for CGST, this is a little bit lower, 0.5 eV. So now to this R or N, you find exponent for crystalline semiconductors. This exponent became one half for direct gap and 2 for indirect gap. And for amorphous semiconductors, towels showed that R is equal to holes, assuming parabolic bands. So now let us look to the properties of different phases of phase change materials. For standard GST225, the band gap in amorphous states it's like 0.7 electron volt. If we increase the temperature, we can go during the different phase transitions. The first phase transition occurs at 160 centigrade, and the band gap is reducing slightly. At 200, we get maybe another different state, disordered state. Then the band gap is reducing further. It's like on the average of 0.5 electron volt, and then just if you approach in the stable phase, the band gap can be gone down to until 0.36 electron volt. So what we can learn from that, we can learn that the band gap depends on the crystal structure of the GST225, and we can use it for different optical or electronic application. Now let us consider the dependence of the optical band gap on the composition. Here, this is optical band gap, and this is the different phases of different composition of phase change materials on these germanium telluride, antimony telluride tie lines. So this is the graph for amorphous phase. This is the graph for cubic phase, which is used for the application. And so what we can see that the band gap in amorphous state of germanium telluride is much larger than for example, for GST 1-4 composition. And in the crystalline phase, it also holds the same, that the band gap is also reducing for germanium telluride. It goes to the GST 1-4, it's also reducing. So we can see that the optical band gap is also compositional dependent, and we can also adjust the band gap of the materials, for example, by doping. If you introduce some oxygen to the material, we can little bit increase the band gap. So if in the undoped state it's 0.68, similar to the GST225. If they increase the doping, this is low level, this is higher level, we can increase the value of band gap up to 0.77 eVolt, and this also holds for the crystalline phases, so we can go here from 0.37 to 0.42. So here you can also tune the band gap of GST materials by doping. But it's not a doping in this case, it's really alloy. So here you create a new alloy based on GST and another composition. This is lanthanum strontium magnesium oxide. So now let us consider also some interesting properties which belongs more to the amorphous materials. This is Urbach tails. Here, if we have disordered materials, we can have some tails which close to the valence band maximum and to the conduction band maximum. And these tails, they are called like Urbach tails. So Urbach tails state they shows and indicates the existence of localized states within the band gap, and it arises from disorder or defects in the material structure. Amorphous materials, they are highly disordered and also have different defects, like maybe voids. And so EU, this is Urbach energy, it measures overall disorder present in a system. And there are different types of disorder which influence the Urbach energy. So it can be like temperature disordering, structural disordering, and it's compositional disordering. So this Urbach tails, this is a function of temperature, structural disordering, and compositional disordering. In the case of amorphous materials, or in crystalline also, you can use optical absorption spectroscopy. This calls Fourier transform infrared spectroscopy, and this is very usable technique to study this parameter U. So now let us look more in detail about this Urbach H. So in amorphous semiconductors, the optical absorption edge is characterized by exponential dependence of the absorption coefficient on photon energy. High absorption region, like more than 10 to the 4 centimeters, involves optical transition between valence and conduction band states, and absorption coefficient of bias-Taos relation, like this, by this equation. And here now we, by measuring the optical band gap, it was a constant, but in this case this is B, which is Taos parameter, and it represents the measure of disorder in the system. And this exponent it's equal to 2. So in the spectral region, like between 10 to 2 and 10 to 4, it's called Urbach's exponential tail region, and it involves low energy absorption, which occurs due to the optical transition between the localized state. So here, if we look to the photon energy, here this is the low energy region. This is the Urbach region range. And the U can be again extracted from the measurement of the absorption in your amorphous material. Now let us look at the dependence of the UU on the composition and the temperature. So at the room temperature, the UU, Urbach energy, it's a compositional dependent, it's decreasing from germanium telluride to the GST 3 to 6. It's also temperature dependent. So it's also decreasing to the 0 Kelvin. So it shows that the disorder in the system is also somehow reducing at 0 temperature. As I said, here was compositional dependent. You can see here the value, it reduces from 0.1 to 0.6, 0.6. Then the B, this is the Taos parameter, which represents also disorder in the system. It's also temperature dependent for GST 2 to 5. For example, it's reducing from low temperatures to the higher temperature. And the band gap is also temperature dependent. Here the Urbach energy is also increasing the temperature. B is also compositional dependent. So for composition 1 to 4, it has low value here, and then it's decreasing to the germanium telluride. This is because this composition that contains more defects than germanium telluride. We will also tomorrow consider the local structure of different phase change materials. So now also interesting parameter, this is the free carrier absorption. The problem with free phase change materials, that the crystalline phase change materials, they contain a large concentration of free carriers, like holes, even at the room temperature. You can identify this from the infrared absorptions in this wavelength range. You can measure the absorption coefficient, and you can see that this coefficient it's high, and it's also reducing compositional dependent. And from the whole measurements, you can identify the carrier density in these materials. So telluride, it has, it's on for all compositions, it's like on the range 10 to the 20 centimeter -3. Compositional dependence, but it contains very high carrier density. And so what does it show? It shows that these materials, they exhibit ametallic p-type conductivity due to this high free carriers in the material. So now I would like to consider photo-induced effect, because it relates to optical properties. And photo-induced effects, it refers to the change of material properties due to exposure to light. And depending on materials, PIs can induce reversible or irreversible changes in the structural, optical, and electronic properties of materials. This effect was shown for a variety of chalcogenide glasses like arsenium sulfide, arsenium selenide, and there are different types of effects. This is like photo-oxidation, photo-darkening, photoablation, photo-induced optical anisotropy, photo-induced crystallization, amorphization, and in the case of phase-change materials, we also consider the photo-induced crystallization and photo-induced oxidation. So the photo-induced crystallization, amorphization, it's based on the phase change between amorphous and crystalline states. So if you illuminate your film with the laser of fluency like in this range and using a very short pulse, 20 nanoseconds, you can induce the crystallization of your material, like here, as deposited amorphous phase, 2 pulses, you have here some crystallites, then further, and you can crystalline your phase, and what you see the change in the properties of your film. This is amorphous state, this is optical reflectivity in dependence on the wavelength, and we can see that the optical reflectivity is changing depending on the volume of the crystalline phase. Like after 2 pulses, it's higher, it's like approaching around 100%. And then this is reversible process. If you apply the laser with higher fluency, like 5 times higher, larger, you can bring back your material to the amorphous state. Here you can see recognize many problems with undoped phase change materials. So first, if there is a volume change up to 10% in the case of germanium telluride, and if it's changing, you can get a high roughness of your material. So you can see, and if you want to use it in the device, it's not good because of contacts. You can lose maybe some contacts up to several switching. So you need maybe to dope the material to reduce this roughness of the film. Next effect, this is photo-oxidation and surface oxide layer. So if you eliminate phase change material by the low light of this this intensity for tens or hours, you can produce oxide layer of several nanometers. But chalcogenides like germanium antimony telluride or antimony telluride, they are known to form this oxide layer even without extensive illumination. So if you take your material outside of the vacuum chamber after the deposition and exposed to the air, you can produce oxide layer on the surface. So you can see here, can be nicely seen by X-based measurements. This was the case of antimony telluride. Here you can see the peaks belonging to the antimony, metallic antimony and tellurium, and you can see also the peaks belonging to the antimony oxide and tellurium oxide. So for the application it's not good because you lose again contact. If you build your device, electric device or optical device, you have oxide in between. To etch away this oxide, you can use like hydrofluoric acid. It's very hazardous, or you can use ion beam etching. For this you need special facility, ion beam facility. But there is very simple method. We used deionized water treatment. So if you put your film in the water for several minutes, you can etch away this oxide layer. So this is after water treatment, and the surface of such treated thin film, it stays like without oxide for several minutes. And this is more than enough to transfer from other camera to another if you want to make contacts on your devices. Another way to overcome this oxide layer is to deposit directly a protective layer in your system. Like if you want to use optical measurements, you deposit material like silicon nitride, silicon oxide, or lanthanum oxide, or similar optically transparent materials, which does not influence the properties of your system much. So, or you can, if you have the possibility to deposit contact for electrical measurements directly in the camera. But this is the one issue with phase change materials. So what does it bring this issue? That the crystallization temperature can be increased, can go higher for uncapped and capped material. So if so native oxide it affects crystallization, so it decreases by temperature, for example, for germanium telluride by 50 centigrade. So this is the crystallization temperature of normal capped germanium telluride. This is for uncapped, so the oxide layer. For GST it also reduces by 20 centigrade. But this is because the crystallization of the material, amorphous materials, it starts from this oxide native layer, so you have additional interface, and so you influence your crystallization kinetic, and in this case also data retention in amorphous states is reduced by the presence of oxide layer, since this oxide promotes crystallization. So this is, I think, that's all what I wanted to say to the optical properties of the phase change materials. So just to sum up this part, so spectroscopic ellipsometry, this is optical technique for measuring of optical constants like NK, band gap, and you can also extract thickness. And UV-Vis spectroscopy is used to acquire absorption spectra like transmission, and to study transmission properties and band gap. So the band gap, optical band gap of different phase change materials composition dependent. For germanium telluride for amorphous it's 0.85, for GST25 it's 0.65, and for crystalline phases there is also a difference. So amorphous phases of phase change materials are less absorptive and reflective than the crystalline phases, and this is the idea of optical devices, different optical reflectivity to use to achieve the device. Also, we saw that the disorder impacts optical properties of phase change and memory materials. We also found that Urbach energy and Tau's parameter are temperature dependent and composition dependent. We also saw some photo-induced effects in phase change materials, which are photo-induced crystallization, amorphization, and photooxidation. And photooxidation results in the formation of oxide layer, which can also be formed after exposure of PCM to air. And this native oxide can be removed by etching, for example, using deionized water. So I think that's all for today. And if you have questions, please ask.
How is the data retention capacity is increasing for amorphous while we are exposed to air? Like I'm also getting the same thing, very low data retention for amorphous phase. So what's happening there actually? I was curious to know. Like amorphous phases, data retention property while exposed to air decreases, you're saying.
Data retention?
Data retention property of amorphous phase is decreasing while oxide layer is...
So, the one problem is this, you have a bad contact to your amorphous state. So you have additional layer and oxide, they have
additional protective layers.
It's insulator, like it's insulator. What do you mean?
Additional protective layer we need, is I was saying like that.
Yeah, but it's for optical properties. If you want to measure optical properties and you want to overcome this formation oxide layer, you should cover this by another oxide layer which is optically transparent in your wavelength range. But if you want to use the electrical switching, of course you don't need to deposit the protective layer. Then you etch the oxide and then deposit contact direct or in another system, like we do this, or you deposit directly in another system the contact. Because in magnetron's pattern you can change different targets and then you can change, you can deposit it. But this is like just to know about this issue. So it's a big issue. Sometimes you want to maybe to make your material in your lab and then transfer to another lab. And then you have to think how you protect the surface, or maybe how I can remove this oxide layer, or maybe I can do the contacts by myself. But sometimes in other labs they have lithography possibility.
Actually, we are using desiccators to transform between labs. Is it a possible way to become oxide on our layer?
Of course, yes. If you just expose to air, this oxide forms very quickly.
Yes.
It was like confirmed by many groups. And also
Yes. Actually, the thing is that is pointing out clearly the way when you are depositing. Okay, so after deposition you just cap with material so that in the same vacuum. So the desiccator way which you are telling, so definitely it will affect. Okay, so for time being you are taking the sample from your system and then you are keeping. So in between it is enough time to get oxides. So in chamber itself, if you just cap, so some capping materials are there, and later on you can some liquid process are there, you can take out also and then you can characterize.
We are using two thermal evaporations for deposition. For deposition is done, we need to take it down. That's the concern.
Okay.
Yeah, so sometimes if you think about photon measurements, sometimes you can go through this oxide layer, or you can think how just to etch a little bit and then deposit another contacts. As I said, just use this sterilized photo. You can adjust the etching time and then you can get the free surface. So it's a problem, but with fresh surfaces you can somehow to manage this problem. But this is a problem.
Any questions, audience? Here I have seen you have done this Urbak energy. So just I'm curious, I'm not aware about that. I mean, when we will design any material and when we are doing related to Urbak, so what we'll get information with Urbak energy? What is it signifies if we are calculating that? So what we can understood with that with Urbak energy?
It's like a measure of disorder in your system.
Okay.
In your amorphous system, you can compare. You can compare. It also says about your localized states.
Local states.
Localized states.
Okay.
How large is it?
Okay.
This tails.
So this stock parameter and this B half value and whatever. So with that we can identify the disorder. How much disorder that material.
Actually, it's just measured, but how to tune these tails, how to make it large or smaller, don't know.
Oh, okay.
So it's compositional dependent, temperature dependent, but it's a basic property of material.
Okay.
So,
Okay.
it's also scales with the thickness of thin film. So it's also changing this Urbak energy. But it's also related to the defects in your system. So maybe some vacancies or some states, the defects, like maybe like grain boundaries of the isomorphous system. There are some maybe clusters. It's,
Thanks. Okay, so if we don't have any question, then just we will wind up our day one session. So we started with the basic of memory, facial memory, and then along with multi-bit level storage and then optical property, device engineering, and all those aspects. Okay, so we will proceed accordingly with our day 2. You can go through with the schedule. So I think our lecture will start again at 10 tomorrow. Okay, so we'll meet again tomorrow. So just try to join at least 10 minutes before so that we can settle down accordingly. Okay, and once again I will tell, if you have any doubt, our speaker is here this week in the guest house, and here also in department E&I also he is sitting. So if you have anything, feel free to discuss. Try to evolve yourself. The thing is that, see, in this level you people are not able to understand, but try to explore. This is my ultimate thing. Okay, but you have to do. Okay, thank you all. Thank you so much.